Electric field. Electrical interaction between charged particles can be reformulated using the concept of electric field. To understand the concept, consider the mutual repulsion of two positive charged bodies as shown in figure. Now, if remove the body B and label its position as point P as shown in the figure, the charged body A is said to produce an electric field at that point and at all other points in its vicinity. When a body B is placed at point P and experiences force F, we explain it by a point of view that force is exerted on B by the field, not by body A itself. The body A sets up an electric field and the force on body B is exerted by the field due to A. An electric field is said to exist at a point if a force of electric origin is exerted on a stationary charged test charge placed at that point. If F is the force acting on test charge Q placed at a point in an electric field, then the electric field at that point is E is equal to F by Q, or F is equal to QE. The electric field is a vector quantity, and since F is equal to QE, the direction of E is the direction of F. A unit of electric field is Newton per Coulomb. Calculation of electric field. In the previous section, we studied a method of measuring electric field in which we place a small test charge at the point, measure a force on it, and take the ratio of force to the test charge. The electric field at any point can be calculated using Coulomb's law if both magnitude and positions of all charges contributing to the field are known. To find the magnitude of the electric field at a point P at a distance r from the point charge Q, we imagine a test charge Q dash to be placed at P. Now we find the force on charge Q dash due to Q through Coulomb's law. F is equal to Q dash by 4 pi epsilon 0 r square. Electric field at P is E is equal to Q by 4 pi epsilon 0 r square. The direction of the field is away from the charge Q if it is positive. Electric field for either a positive or negative charge in terms of unit vector r directed along line from charge Q to point P is E is equal to Q r cap by 4 pi epsilon 0 r square. R is equal to distance from charge Q to point P. When Q is negative, direction of E is towards Q, opposite to R. Electric field due to multiple charges. Consider the number of point charges Q1, Q2 and so on, which are at distance R1P, R2P, and so on from point P as shown in figure. The resultant electric field is the vector sum of individual electric fields, as E is equal to E1P plus E2P plus and so on. E is equal to 1 by 4 pi epsilon 0 into Q1 by R1p square, R1p cap plus Q2 by R2p square, R2p cap plus and so on. This is also a direct result of the principle of superposition discussed earlier in case of electric force on a single charge due to system of multiple charges. E is a vector quantity that varies from one point in space to another point and is determined from the position of square charges. Electric field lines, since electric field varies as inverse of square of the distance that points from the charge, the vector gets shorter as you go away from the origin, and they always points radially outwards. Connecting up these vectors to form a line is a nice way to represent this field. The magnitude of the field is indicated by the density of the field lines. Magnitude is strong near the center, where the field lines are close together, and weak farther out, where they are relatively apart. So the electric field line is an imaginary line drawn in such a way that its direction at any point is same as the direction of the field at that point. Field lines of a single positive charge points radially outwards, while that of a negative charge is radially inwards, as shown below in the figure. Field lines around the system of two positive charges give a different picture and describe the mutually repulsion between them. Field lines around a system of a positive and negative charge clearly shows the mutual attraction between them, as shown below in the figure. Field lines around the system of single two positive charges give a different picture outward and describe the mutually negative charge between them is radially inwards, as shown below in the figure. Field lines around a system of a positive and negative charge clearly shows the mutual attraction between them, as shown below in the figure. Some important general properties of field lines are: 1. Field lines start from positive charge and end on a negative charge. 2. Field lines never cross each other. If they do so, then at the point of intersection, there will be two directions of electric field. 3. Electric field lines do not pass through a conductor. This shows that the electric field inside a conductor is always zero. 4. Electric field lines are continuous curves in a charge-free region. Electric flux. Consider a plane surface of area del S in a uniform electric field E in the space. Draw a positive normal to the surface and theta be the angle between electric field E and the normal to the plane. Electric flux of the electric field through the chosen surface is then del phi is equal to E del S cos theta. Corresponding to area delta S, we can define an area vector del S of magnitude del S along the positive normal. With this definition, one can write electric flux as del phi is equal to E dot del S. Direction of area vector is always along normal to the surface being chosen. Thus, the electric flux is a measure of lines of forces passing through the surface held in the electric field. Special cases. If E is perpendicular to the surface, that is, parallel to the area vector, then theta is equal to 0 and del phi is equal to E dot del S cos 0. If theta is equal to pi, that is, electric field vector is in the direction opposite to area vector, then del phi is equal to minus E del S. If electric field and area vector are perpendicular to each other, then theta is equal to pi by 2 and del phi is equal to 0. Flux is a scalar quantity and it can be added using rules of scalar addition. For calculating total flux through any given surface, divide the surface into small area elements. Calculate the flux at each area element and add them up. Thus, total flux phi through a surface S is phi approximately equal to summation of E dot del S. This quantity is mathematically exact only when you take the limit del S tends to 0, and the sum in equation 3 is written as integral phi is equal to integration of E dot ds.